Good morning, everyone. Today, we embark on an exploration of a topic that is both dynamic and far reaching: technological change.
This formidable force is responsible for reshaping industries, transforming economies, and altering the balance of power among nations. However, it is crucial to understand that technological change is neither automatic nor accidental. It follows discernible patterns, involves a multitude of actors, and is profoundly influenced by policies, institutions, and societal factors. To begin our journey, let us delve into the pivotal roles played by research conducted within universities and public laboratories, particularly in aiding nations in their quest for economic catch-up. In many developing countries, the capacity to bridge the gap with industrialized nations hinges on their ability to construct robust scientific and technological capabilities. Universities and public research institutions stand at the heart of this endeavor. They serve not only as centers for education but also as hubs for both basic and applied research, which are essential components of innovation systems. Consider, for instance, the post-war period when nations such as South Korea and Taiwan made strategic investments in university-based research and development (R&D). This deliberate effort was aimed at building domestic capabilities in critical areas like semiconductors, electronics, and materials science. These public institutions became the breeding ground for talent and technical expertise, which subsequently empowered local industries to flourish and innovate. In today's knowledge-driven economy, the interplay between academia and industry has assumed greater significance than ever before. Through collaborative partnerships, technology transfer offices, startup incubators, and joint research programs, universities contribute to vibrant innovation ecosystems that bolster national development and competitiveness. Next, let's unravel the process of technological change through the lens of diffusion. An innovation does not realize its full potential the moment it is conceived. Its true value emerges when it is diffused, when it permeates across users, industries, and society at large. The diffusion process captures how, when, and why new technologies are embraced by users over time. Everett Rogers, in his seminal work on the diffusion of innovations, categorized adopters into distinct groups: innovators, early adopters, early majority, late majority, and laggards. Adoption is influenced not solely by the inherent benefits of the technology but also by factors such as social influence, compatibility with existing systems, and perceived risks. For instance, while smartphones rapidly proliferated across the globe, certain populations delayed adoption due to factors like cost, infrastructure limitations, or digital literacy barriers. Understanding the diffusion process equips businesses and policymakers to strategically plan for market entry, infrastructure development, and educational campaigns. To gain deeper insights into the evolution of technology, we turn to modeling technological change. One widely utilized tool is the technology S-curve. This model illustrates that technological performance over time follows an S-shaped trajectory. In the initial phase, progress is sluggish as experiments falter and challenges are addressed. During the growth phase, performance surges dramatically due to learning and breakthroughs. Finally, in the maturity phase, gains decelerate and the technology approaches its physical or economic limits. The S-curve serves as a valuable guide for managers, helping them decide when to continue investing in existing technologies and when to pivot towards newer alternatives. Companies that fail to recognize the plateau of a mature technology often miss opportunities to lead the next wave of innovation. Now let's explore the linear model of innovation, a traditional perspective that suggests innovation commences with basic research, flows into applied research, progresses through development, followed by production, and ultimately culminates in market adoption. While this model proved useful for understanding innovation in science-intensive industries like pharmaceuticals or aerospace, it falls short in capturing the complexity of modern innovation, which tends to be non-linear, networked, and interactive. This is where alternative perspectives come into play. One such perspective is actor network theory, ANT. ANT views technology as the outcome of relationships among various actors, not limited to individuals but encompassing machines, institutions, laws, and even ideas. Innovation emerges from interactions within this intricate network. For example, a new medical device succeeds not solely due to its design but also because of regulatory approvals, hospital procurement systems, and patient acceptance. Another significant theory is the social shaping of technology, SST. This concept posits that technology is not merely a product of scientific logic or market demand, it is molded by social, political, and cultural contexts. For instance, the design of public transportation systems depends not only on engineering principles but also on public attitudes, city planning, and political will. Next, let's delve into the concept of open innovation, a paradigm that departs from the notion that innovation must be confined within internal boundaries. In open innovation, firms leverage both internal and external ideas, collaborating with universities, startups, competitors, and even customers. This model reflects the reality that knowledge is widely distributed and no single company holds a monopoly on good ideas. Complementing this is the concept of user innovation. At times, the users themselves become the innovators. They modify, enhance, or even create new solutions to address problems that suppliers may overlook. A compelling example is how extreme sports athletes redesign their gear, or how open source programmers develop tools that the market never anticipated. Companies today increasingly harness this bottom-up innovation by engaging with lead users and user communities. Finally, we must acknowledge the pivotal role of policy in shaping technological change. Governments are not mere passive observers, they actively influence the direction, pace, and impact of technological change. They achieve this through funding research, establishing regulations, providing tax incentives, and creating infrastructure. Policy decisions can expedite the adoption of green technologies, support national digital strategies, or promote inclusiveness in access to innovation. For instance, policies that subsidize solar energy or mandate fuel efficiency standards directly shape the trajectory of technological growth. Effective policy encompasses both supply-side interventions, such as R&D, funding, and education, and demand-side measures, such as public procurement or awareness campaigns. Importantly, policy must be adaptable, recognizing that technology evolves rapidly and that rigid rules may impede innovation rather than facilitate it. In conclusion, technological change is a multifaceted process. It encompasses science and society, markets and politics. It is neither linear nor automatic. It is shaped by how we manage knowledge, support institutions, model growth and design policies. For innovation to thrive, we must comprehend not just how technology functions, but how it disseminates, who influences it, what conditions nurture it, and when to abandon old models in favor of embracing new paradigms. Thank you for your attention. In our next session, we will delve into national innovation systems and explore how countries build capacity to innovate, compete, and transform.